Okay, let's go ahead and take a look at some problems with double slit diffraction. You can see the equations up top. Now what I'm going to do is I'll read through the question and I'll give you a moment. You can just hit pause on your player there. Try to solve the problem yourself and then hit play and watch as I solve it and make sure we get the same things. So this first problem says, at what angle will you find the first order maximum for a 450 nanometer blue light falling on double slits with a separation of 0.1 millimeters? Okay, well, now in this case I'm looking for the angle. We only have one equation for angle, and that's this equation on the left over here. And so I'm going to write that equation down, and lambda equals d sine theta. Now I'm solving for theta, and so I can divide the d there inverse sine of both sides. That's going to help us get rid of the sine because the inverse sine of sine is simply theta. And from there, it's just a matter of working out the math. Inverse sine, n, remember n is any whole number. In this case, the problem says it wants the first order maximum. The first order maximum has an n value of 1. The lambda here is the wavelength. We're given the wavelength of 450 nanometers. That's times 10 to the negative 9th meters. Divided by the distance between the slits, it's in millimeters. So I need to make sure to say times 10 to the negative 3rd meters. And we just go through and do the math now. Get pCalc up here. So that is 450 times 10 to the negative 9th divided by 0.1 times 10 to the negative 3rd. And if I take the inverse sine of all that, we're going to get an angle of 0.26 degrees. That is the angle of the first maximum in this situation. Now the second pattern we're going to do looks at this. Looks at the same graphic we've seen before. And now what I've made a few adjustments to this pattern. First of all, we're going to say the distance from the slit to the screen is 5 meters. We're going to say the wavelength of light is 480 nanometers. And the position that we see on the x-axis, those will be in millimeters. And so I want to find two things. I first want to find the slit width. What is the width of each one of those slits that makes up that double slit pattern? Second thing I want to find is the distance between slits. Okay, so slit width. So give you all a moment to solve this. Hit pause. Try to find both of those. Be back in a second. All right, to find the slit width, we're first going to look at the single slit envelope. This is the envelope right here. And to really look at the envelope, we're going to think about the equation theta equals lambda over b, which also equals x over d. Remember, x is that spacing to the first minimum. Spacing to the first minimum. In this case, we have, this is our first minimum right here. And if I look at the graph, it looks like that's going to be about, let's see, was that 12.5? 12.5 meters. So rearranging to solve for b, b equals lambda d over x. We know the wavelength is 480 times 10 to the negative 9th meters. Distance of the screen is 5 meters. And x, we just saw, is about 12.5 millimeters or so. 10 to the negative 3rd. Again, doing our math, 480 times 10 to the negative 9th times 5 divided by 12.5 times 10 to the negative 3rd. And I find that the slit width in this situation is going to be about 1.9 times 10 to the negative 4th meters. So we're looking right at about 0.2 millimeters. 0.2 millimeters. Again, for slit width, we use the single slit envelope. Now, to find the distance between the slits, because this is a double slit pattern after all. In this case, well, we don't have an angle, and so I'm going to go ahead and use the equation from topic 4.4. S equals lambda capital D over lowercase d. Now, distance between the slits is lowercase d. So d equals lambda capital D over s. The wavelength, again, 480 times 10 to the negative ninth meters. Distance still 5 meters. Over the spacing. Now, I need s. I need the spacing of the fringes. Really, I could pick any two fringes. I think the easiest ones to do, or just pick the middle one. Starts at 0. That's easy. And go to the first. And that looks like a spacing of about, what is that, 2.5. Let's go with 2.5 times 10 to the negative 3 meters. And to use my calculator again, we're going to say 480, oops, clear everything here. 480 times 10 to the negative ninth, multiplied by 5, divided by 2.5 times 10 to the negative third. And I'm going to get the distance between the slits is equal to 9.6 times 10 to the negative fourth meters, or about a millimeter. The two slits are about a millimeter apart. These are two examples of pretty straightforward double slit diffraction problems. With that, you can then sort of move to that worksheet that's going to have you take a look at some IB type problems with double slit problems. We'll follow this up the next class with multiple slits. What happens when you get 3, 4, 5, 6, 7, 8, and so on. And also we're going to take a look at diffraction gratings. How do we measure things with diffraction gratings? How are they used? And how can we tell what material something is using a diffraction grating? Hope all is well. Until I see you next, this has been Mr. Reynolds with double slit diffraction problems.